Welcome to the deep dive. Today, we're not just dipping our toes in. We're taking a full headfirst plunge into one of the most thrilling and fastest changing frontiers in AI, the world of AI agents.
That's right.
You've undoubtedly followed the incredible surge in large language models, their prowess in planning, reasoning, and, well, natural language understanding has fundamentally reshaped our capabilities.
Absolutely. The progress has been stunning.
But what's truly captivating now is the profound shift we're witnessing, moving beyond manually configured static AI systems towards something far more autonomous. We're talking about agents that can not only adapt but continuously improve themselves, almost evolving like living systems.
You've hit the nail on the head. This isn't just an incremental improvement. It's really a fundamental paradigm shift in how we conceive and deploy AI. Our guide for this deep dive is a fantastic foundational survey paper titled The Evolution Landscape of AI Agents, which you can find on ArcFIFT. It gives us a comprehensive roadmap and, importantly, a clear conceptual framework for understanding this whole new landscape of self-evolving AI.
A framework is definitely needed here.
It is. And for those of you who like to get your hands dirty, the associated GitHub repository, it's Evo Agent X Awesome Self-Evolving Agents, is an excellent resource for practical exploration of these concepts.
Great resource. So let's unpack this core challenge that makes self-evolving agents not just an innovation, but, well, a necessity.
Okay.
Most of our current AI agent systems, whether they're single or multi-agent, they rely on manually designed static configurations. Once deployed, their architectures and functionalities are largely fixed.
Very much set in stone.
Exactly. It's like designing a specialized machine that can only do one job perfectly for one specific scenario.
And that's where the real-world friction arises. Because environments are anything but static. User intents are constantly shifting, task requirements evolve, and external tools or information sources are in perpetual flux.
Always changing.
Always. Imagine a sophisticated customer service agent. It's perfectly trained on existing products and policies. But what happens when the company launches a whole new product line or updates its return policy? If that agent is static, it's essentially stuck in the past, giving out wrong information. Or worse, just saying, I don't know. Or think about a scientific research assistant trying to incorporate a brand new algorithm or integrate a novel analysis tool into an existing workflow. Well, that could be a nightmare if it's not designed to evolve.
That's a huge operational barrier. The manual effort involved in constantly reconfiguring these systems every time something changes. It's not just time-consuming and labor-intensive. It's completely unscalable for the kind of complex, dynamic problems we're asking AI to solve.
Totally unscalable.
So this concept of self-evolving AI agents is really a necessity, isn't it?
Absolutely. The paper formally defines these agents as autonomous systems that continuously and systematically optimize their internal components through interaction with their environments.
Okay, continuous optimization.
Right. Their goal isn't just to adapt to changing tasks, contexts, and resources, but crucially, to do so while simultaneously preserving safety and enhancing performance. This isn't just about getting better, it's about getting better responsibly.
Getting better responsibly. I like that. What's truly fascinating here are the guiding principles for these systems, drawing inspiration from Isaac Asimov's foundational 3 laws of robotics.
Yes, a really interesting connection.
The authors of this paper have proposed their own 3 laws of self-evolving AI agents, and they're hierarchical, just like Asimov's, acting as guardrails for this continuous improvement.
Crucial guardrails.
The first law, endure, emphasizes safety adaptation. Agents must maintain safety and stability during any modification, no matter how ambitious the change. Safety first.
Safety first, absolutely. Following that, the second law is excel, which mandates performance preservation. Critically, and this is subject to the first law, agents must preserve or enhance existing task performance.
So no breaking things while trying to improve.
Exactly. You can't improve in one area if it means degrading your core function, or worse, becoming unsafe. And then the third law, evolve, dictates autonomous evolution. Subject to both the first and second laws, agents must be able to autonomously optimize their internal components in response to changing tasks, environments, or resources.
That hierarchy makes a lot of sense. Endure, then excel, then evolve.
It provides a clear structure for responsible autonomy.
So what does this all mean for the broader landscape of AI, especially for those of us working with LLMs? The paper characterizes this monumental shift as a 4-stage trajectory in LLM-based systems, really showing how we've progressed.
It maps it out quite nicely.
It begins with MOP, or Model Offline Pre-Training. This is where models are pre-trained on vast static corpora and then deployed in a fixed frozen state. There's no further adaptation or learning once they're out in the wild.
Right, the classic train once, deploy forever model.
Pretty much.
Then we move to MOA, Model Online Adaptation. Here, post-deployment updates are introduced. This involves techniques like supervised fine-tuning, using low-rank adapters, LoRi, or reinforcement learning from human feedback, RLHF, all driven by labels, ratings, or instruction prompts.
So the model can learn after deployment now?
Yes, the model is no longer entirely static. It can learn after deployment, but usually requires explicit, curated feedback. It's not fully autonomous learning yet.
Okay. Building on that, we have MAO, multi-agent orchestration. So if MOA is about one model adapting, MAO takes it to the next level by coordinating teams of LLM agents.
Right, bringing teamwork into the picture.
They communicate and collaborate through message exchanges or even sophisticated debate prompts to tackle complex tasks. The fascinating part is they do all this without fundamentally changing the core LLM model parameters themselves. It's all about clever teamwork and dynamic communication rather than direct model retraining.
It's orchestration, not evolution of the core model. A very clever way to get more complex behavior without retraining everything.
Exactly.
And finally, we hit MAA's multi-agent self-evolving. This is the true apex, the holy grail, perhaps, where agents don't just adapt, they continuously self-re-engineer.
Self-re-engineer. Wow.
Yeah, they're refining their own prompts, their memory structures, how to use tools, even their inter-agent communication patterns, all based on what they learn from interacting with the environment and receiving meta rewards. It's the moment autonomous evolution stops being a theoretical concept and starts becoming a living reality.
That's a huge leap. So in this deep dive, you're going to gain a truly comprehensive and systematic understanding of existing techniques for these self-evolving agentic systems.
We'll cover the landscape.
We'll unpack a unified conceptual framework for understanding agent evolution, dive into detailed insights on single agent, multi-agent, and domain-specific optimization, and explore the key challenges and promising future research directions.
Yeah, we'll touch on the challenges too, which are significant.
Our mission today is to offer you valuable insights and guidelines for developing more effective and sustainable agentic systems, providing you with, hopefully, a shortcut to being well-informed on this critical, cutting-edge topic that is reshaping the future of AI.
Let's dive in.
All right, so we've established this incredible vision for lifelong, self-evolving agent systems that truly endure, excel, and evolve. But to understand how they get there, we first need to strip it back to basics. What exactly is an AI agent, and what are its fundamental building blocks?
Good place to start.
Let's start by looking at foundations of AI agent systems, beginning with single-agent systems. What exactly defines an AI agent in this context?
Well, at its core, you can think of an AI agent as an autonomous system. It perceives its surroundings, it reasons about its objectives, and then it acts within that environment to get things done, to achieve its goals.
Perceive, reason, act. The classic loop.
Exactly. And while our discussion often defaults to LLMs as the central intelligence, it's really important to remember that these architectural principles readily generalize to other foundation models, whether they are vision language models or models for protein folding or even robotics. It's a broader concept.
Right, the principles apply widely, so it's about more than just the language model. It's about putting that intelligence into action. What are the core components that enable an agent to achieve this autonomy?
There are several critical modules that work in concert. First and central is the foundation model itself, often an LM, as we said. This acts as the core reasoning engine, responsible for interpreting instructions, developing plans, and executing actions.
The brain, so to speak.
Kind of, yeah. Supporting this, we have the perception module, which is tasked with acquiring and interpreting environmental information. This could be textual inputs, audio, video, sensor data, anything it needs to build a meaningful internal representation for reasoning.
So the senses of the agent.
Precisely.
That makes perfect sense. The agent needs to understand its surroundings. Then, once it perceives, how does it figure out what to do? That's where the planning module comes in, guiding its actions, correct?
Exactly. The planning module allows an agent to decompose complex tasks into actionable subtasks or sequences of operations, guiding their execution over multiple steps. You need a plan.
Makes sense.
The simplest approach is something like chain of thought prompting, where an agent breaks down a problem into a straightforward sequence of steps, almost like following a recipe.
Step by step.
But as tasks get more complex, that linear path can become a bottleneck. It's often too simple. So, more dynamic approaches, such as the React framework, interleave planning, and execution, allowing the agent to revise its plans based on real-time feedback from the environment.
Ah, so it can adjust on the fly.
Yes, which is crucial. Beyond linear, we also see branching strategies like tree of thought and graph of thought, where an agent explores multiple reasoning paths simultaneously. This is really key for tackling ambiguous or highly complex problems where there isn't one obvious path forward.
Exploring possibilities, that's a significant evolution from just following a predetermined path. And speaking of ongoing tasks, memory must be crucial for consistency, preventing the agent from forgetting its past actions or context. Tell us about the memory module.
The memory module is absolutely vital. It's needed for retaining and recalling past experiences, supporting context-aware reasoning, and maintaining consistency over time. You don't want your agent to forget what it did 2 steps ago.
Definitely not.
It's typically bifurcated into short-term memory, which stores context and interactions for the current task. Think of it as the agent's scratchpad, often discarded upon task completion, and long-term memory.
Okay, short-term and long-term.
Right. Long-term memory persists over time, accumulating broader knowledge, past experiences, or reusable information across various tasks.
So how does an agent efficiently access that long-term knowledge, especially when its immediate context window, the LLM's input limit, is constrained?
That's a key challenge.
Okay.
A common and incredibly effective mechanism is retrieval-augmented generation, RAG.
Yeah.
Probably heard a lot about RAG.
Yes, it's everywhere.
Here, agents retrieve relevant information from their long-term memory, perhaps a vector database of past experiences or a knowledge base, and then integrate that information directly into the LLM's input context.
Injecting knowledge right when it's needed.
Exactly. Now, RA is a game changer for bringing external knowledge into the LLM's context.
Right.
But as anyone who's worked with large datasets knows, just having the data isn't enough. The real challenge is, how do you design that memory effectively? How do you decide what to store, when to store it, and most importantly, how do you retrieve it efficiently and seamlessly integrated into the agent's live reasoning without it feeling clunky or slow? These are all really tricky active research areas right now.
Yeah, optimizing that retrieval and integration seems non-trivial. So an agent has its brain, its senses, and its memory. But to truly operate in our complex world, it needs hands and feet. It needs to do things. And that's where tool use becomes absolutely indispensable, isn't it?
It truly is. Tools are indispensable for AI agents operating in real-world scenarios. LLMs, despite their immense power, are inherently limited by their static training data and lack of real-time interaction capabilities. They can't, browse the web on their own.
They need help.
Tools extend an agent's functional scope exponentially, enabling it to interact with external systems like web search engines, code interpreters, browser automation frameworks, or even specialized APIs for scientific instruments. The process typically involves the agent selecting the right tool for a given subtask, constructing the appropriate input for that tool, making API calls, and then critically integrating the tool's output back into its ongoing reasoning process.
Closing the loop with the real world.
Precisely. This tool integration is a critical interface, transforming a language model from just a text generator into an active participant in its environment.
Okay, that gives us a solid picture of a single agent. Now let's explore how intelligence scales up with multi-agent systems, or MAS. What's the core motivation behind MAS, and why are they becoming so important for tackling real-world problems?
The motivation is quite clear and compelling. Many real-world tasks, especially highly complex or open-ended ones, simply exceed the capabilities of a single monolithic agent. They're just too big or multifaceted.
Too much for one agent to handle.
Exactly. These tasks often require diverse specializations, parallel processing, and complex coordination that a lone system cannot provide. Multi-agent systems mirror distributed intelligence found in biological and social systems, acting as a collection of autonomous agents interacting in a shared environment to achieve goals that are far beyond any single agent's reach.
So it's about harnessing collective intelligence, like a team. What are the key concepts that define how these agents work together and enable that synergy?
2 key concepts stand out. First is agent topology, which refers to the structural configuration defining how agents are connected and how they communicate. Think of it as the org chart or network structure.
Who talks to whom?
Exactly. This directly influences information flow, dictating who talks to whom and how tightly coupled their collaboration is. Then there's the multi-agent workflow, which orchestrates these interactions to achieve complex shared goals.
The process they follow.
Right. The critical insight here is that when multiple agents collaborate effectively through such well-designed workflows, the system's overall performance can often exhibit emergent properties and exceed the sum of their individual capabilities. The whole is greater than the sum of its parts.
That's a powerful idea. What are the specific tangible advantages that MAS offers over single-agent systems for you as a practitioner? What makes them worth the extra complexity?
The advantages are significant for real-world deployments. First, MAS excel at task decomposition, breaking down highly complex problems into manageable subtasks that can be assigned to specialized agents, improving overall efficiency and focus.
Divide and conquer.
Precisely. Second, they inherently support parallel execution, allowing multiple agents to work simultaneously on different parts of a problem, which greatly accelerates problem-solving vital for time-sensitive applications.
Faster results.
Definitely. Third, their decentralized nature enhances robustness. If one agent fails, others can often dynamically redistribute tasks or compensate, leading to graceful degradation rather than system collapse. This fault tolerance is invaluable.
That's a big one. Reliability. And I imagine scalability is a big factor here too, especially in expanding or adapting to new challenges.
Absolutely. MAS offers inherent scalability, as new agents can be seamlessly integrated into an existing system without requiring a complete redesign. This flexibility is critical for dynamic environments.
Easy to add more capacity or skills.
Yes. Finally, collaborative mechanisms like structured debate and iterative refinement enable MAS to generate more innovative, diverse, and often more reliable solutions by leveraging those diverse perspectives. Different agents bring different strengths.
Makes sense.
And the good news is, frameworks like Camel and AutoGen have significantly streamlined the development of these systems, providing modular architectures, role-playing capabilities, and automated orchestration, making them more accessible for development. They're taking some of the pain out of building these.
That's good to hear. Moving from the why to the how, let's talk about the system architecture for MAS. The paper highlights that hierarchical structures are a prevalent and effective approach.
Hierarchical structures are quite common, yes. In multi-agent systems, you often see a static, almost organizational chart-like setup. Think of it like a company with clear departments or a reporting structure.
Okay.
Tasks are explicitly broken down and then assigned sequentially to specialized agents, just like a project manager assigning tasks to team members. MetaGPT, for example, uses standard operating procedures to streamline entire software development pipelines within such a structure. Halo incorporates Monte Carlo tree search to enhance reasoning within its hierarchy.
Interesting examples.
This approach is prevalent in fields like software development, medicine, scientific research, and social sciences, due to its modularity and how well it supports domain-specific optimization by clearly delineating responsibilities. It's just a very organized way to manage complexity.
And how do these agents actually talk to each other within these structures? What are the key communication mechanisms that ensure effective collaboration and avoid, misunderstandings or inefficiencies?
Communication is paramount, absolutely. The quality of it often dictates system performance. One highly effective approach is structured output, where agents use formal formats like JSON, XML, or even executable code for their messages.
Not just natural language chats.
Right. This ensures high machine readability, interpretability, and cross-platform collaboration, which is ideal for applications demanding precision and efficiency, especially in complex problem-solving and reasoning tasks. The compact information representation also significantly boosts computational efficiency, which is a major concern in large-scale MAS. Less fluff, more substance.
I see. So clear, standardized formats are crucial for machine-to-machine interaction. What about more advanced interoperable ecosystems, almost like an internet for agents? That sounds quite futuristic.
It does, but it's where things are heading. For that, we're seeing the emergence of standardized protocols designed to enable true interoperability between different agent systems. A2A, for instance, standardizes horizontal peer-to-peer task delegation, ensuring agents can seamlessly pass tasks to their peers.
Peer-to-peer delegation.
Yes. ANP, the Agent Network Protocol, aims to build a secure, open, decentralized agent internet. It's got built-in decentralized identity. Imagine each agent having its own verifiable digital passport and dynamic protocol negotiation so they can figure out how best to talk to each other on the fly.
Wow, DID for agents.
Yeah. MCP, the Model Context Protocol, standardizes vertical communication between agents and external tools or data resources. And then there's Agora, a meta protocol for horizontal communication, enabling agents to dynamically negotiate and evolve their communication methods, switching between natural language and structured routines based on context.
Adapting how they talk.
Exactly. These protocols are foundational for truly interoperable and flexible agent ecosystems, pushing us towards that MAC vision we talked about.
This all leads us to that grand vision: lifelong, self-evolving agentic systems, MAA. We've talked about MOP, MOA, and MAO reducing manual configuration, but the paper argues that even advanced multi-agent frameworks still have fundamental limitations. How does MACE bridge this gap and truly close the loop?
Well, even those advanced multi-agent frameworks like AutoGen or Camel often rely on handcrafted workflows, fixed communication protocols, and human-curated toolchains. These static elements fundamentally constrain adaptability. They make it incredibly difficult for agents to maintain performance in dynamic, open-ended environments where requirements, resources, and goals are constantly shifting.
Still too rigid.
Exactly. And MA addresses these limitations head-on by closing the loop between initial deployment and continual autonomous improvement. It essentially allows the system to learn and adapt perpetually, modifying its own structure and behavior.
This is where the rubber really hits the road. We've talked about the three laws. In theory, endure, excel, evolve. But how do they actually guide the design and ongoing operation of these lifelong, self-evolving systems? What does it mean when these agents are actually in the wild?
Right, they're not just abstract ideas. The three laws become core prescriptive design principles for MAES. These systems are engineered to continuously monitor their own performance and safety during operation, acting as internal auditors.
Self-monitoring.
Yes. They are designed to preserve or enhance capabilities through controlled incremental updates, ensuring that improvements in one area don't inadvertently break existing functionality or introduce new risks. That's the excel part, subject to endure.
Controlled updates.
And critically, they must autonomously adapt prompts, memory structures, tool use strategies, and even the inter-agent topologies in response to shifting tasks, evolving environments, and changing resources. And all of this while adhering strictly to the first two laws of safety and performance preservation. That's the evolve part.
So it's about moving beyond handcrafting every single interaction pattern or system component. These systems can essentially generate, evaluate, and refine their own configurations.
That's the goal.
That's a huge shift from static executors to continually learning participants, transforming the very nature of AI engineering, wouldn't you say?
It is transformative, absolutely. And the implications are far-reaching. This vision reshapes how we approach many complex domains. Imagine scientific discovery where agent ecosystems autonomously generate hypotheses, design experiments, analyze results, and iterate on research workflows, constantly refining their approach.
Wow, automated science iteration.
Or in software engineering, where agents co-evolve development pipelines, seamlessly integrating new tools and methodologies as they emerge, adapting to new languages or frameworks automatically.
Keeping pace with tech changes.
Exactly. Even in human-AI collaboration, they could learn individual user preferences and continuously personalize interaction styles, becoming genuinely intuitive assistants that adapt to you.
That's fascinating. And it extends beyond the purely digital realm, too. Interfacing with the physical world through robotics, IoT devices, cyber-physical infrastructures.
Right, perceiving environmental changes, acting upon them, and incorporating real-world feedback directly into their evolutionary loop. The ultimate goal, as the paper eloquently puts it, is scalable, sustainable, trustworthy AI systems that live, learn, and last.
Live, learn, and last. That's quite a statement.
It is. It's not just an ambitious outlook. It's becoming an imperative for the next generation of AI.
Now, to truly grasp the mechanics of these self-evolving agents, we need a common language and structure. Let's move into a unified conceptual framework for May. How does the paper abstractly describe this self-evolving process? It sounds like a continuous loop.
It is fundamentally characterized as iterative optimization, yes, a continuous feedback loop driven by performance evaluations and environmental interactions. It always begins with a clear task specification.
Okay, starting point.
This includes the initial inputs, the desired goals, any operational constraints, and potentially a set of guiding examples. These elements collectively define the problem an agent needs to solve and the parameters within which it must operate.
Defining the sandbox it plays in.
Essentially, yes.
Okay, so it starts with defining the problem and its boundaries. Then, what are the core abstract key components of the optimization process itself that make up this continuous loop? The paper breaks it down, right?
It does, into four fundamental components. First, we have system inputs. This encompasses all the contextual information and data provided to the optimization system. It defines the task requirements, any hard constraints, and the available data that the agent will use.
The raw materials.
Exactly. These inputs can vary widely depending on the scenario, from a simple natural language query to complex multimodal sensor streams. It's essentially the what of the problem the agent is facing.
And the who or what that's being subjected to this optimization would be the agent system, correct, the thing being improved.
Precisely. This is the system being optimized, the individual agent, or the multi-agent collective. It's the entity that perceives the system inputs, executes actions in response, and generates outputs. This is the component undergoing refinement and evolution.
Then we have the environment, which sounds like it provides the real-world context and, crucially, the feedback on the agent's performance. How well did it do?
Indeed. The environment is the external context where the agent operates.
Yeah.
This can range from highly controlled benchmark datasets to dynamic, unpredictable, real-world settings, for instance, a code execution environment with compilers and interpreters for programming tasks.
Right.
Or literature databases and simulation platforms for scientific research. Crucially, the environment generates feedback signals derived from evaluation metrics like accuracy, F1 score, or success rate, which quantitatively measure the agent's effectiveness against its goals.
Quantifiable feedback. But what if that ground truth data or a clear objective metric isn't readily available, which, let's face it, is often the case in complex open-ended tasks?
Right.
How does evaluation happen then?
That's a great question. In such cases, LLM-based evaluators are often employed. These systems leverage powerful LLMs to act as judges, generating proxy metrics or providing detailed textual feedback by assessing correctness, relevance, coherence, or alignment with task instructions.
Using an LLM to judge another AI.
Exactly. This provides a crucial, albeit potentially imperfect, signal for the optimization process, even without direct human labels or clear objective functions. It's a way to get some feedback signal.
Finally, we have the optimizers. This is where the magic of self-evolving truly happens, isn't it? It's the engine of change, the component driving the improvements.
The optimizer is, as you say, the core component of the self-evolving feedback loop. It's responsible for refining the agent system, based on the feedback received from the environment. Its ultimate objective is to find the agent configuration that achieves the best possible performance.
The best version.
Right. Formally, this is often expressed as A = argmax ASOAA, where S represents the search space of all possible agent configurations, and OAAI is the evaluation function that maps the agent's performance given the inputs to a scalar score. Basically, find the A in the space S that maximizes the outcome O.
Okay, maximizing performance over search space. So an optimizer itself has two core components: the search space it explores and the algorithm it uses to navigate that space.
Exactly. The search space S defines the entire set of agent configurations that can be explored. This could be anything from the specific phrasing of prompts to tool selection strategies to continuous LLM parameters or even fundamental architectural structures of multi-agent systems. It's the universe of possibilities.
And the optimization algorithm H is how it explores that universe.
Precisely. It specifies the strategy used to explore this space S. This could involve rule-based heuristics, gradient-based methods, Bayesian optimization, Monte Carlo tree search, reinforcement learning, evolutionary strategies, or even learning-based policies. The pair, SH, the space, and the search strategy dictates how efficiently and effectively the system can adapt and learn.
Different tools for different search jobs.
Absolutely. The paper further categorizes these optimizers based on whether they're designed for single-agent, multi-agent, or highly domain-specific systems, each presenting distinct characteristics and challenges in their design.
Now, let's delve into single-agent optimization, focusing on enhancing the capabilities of an individual agent without scaling up to multiple entities. The goal here is improving performance by targeting specific components within that single-agent system.
Right, honing the individual.
We'll start with LLM behavior optimization, which aims to directly improve the model's reasoning and planning abilities. Why is this needed, given how good LLMs seem already?
Well, the motivation for this is clear. While LLMs are incredibly fluent in language, there's often a discernible gap between their linguistic competence and their ability to perform complex, multi-step reasoning, critical decision-making, and robust planning required for sophisticated agentic tasks. They can talk the talk, but need help walking the walk sometimes.
Okay, bridging that fluency versus reasoning gap. How are researchers addressing this? The paper primarily discusses two major approaches within training-based behavior optimization.
Indeed. This involves reasoning-oriented training through supervised fine-tuning, SFT, and reinforcement learning, RL. For SFT, the idea is to provide explicit examples of good reasoning. Show, don't just tell.
Learning by example.
Exactly. Examples include STAR, TORA, and NEXT, which systematically train models on high-quality reasoning traces, essentially teaching them how to think, better step by step. For RL, we see approaches like self-rewarding, DeepSeek Prover v1.5, and Absolute Zero, where models learn to refine their responses and internal reasoning processes through systematic feedback or rewards. This can be much more scalable than manually labeling every single reasoning step.
Learning from trial and error, guided by rewards.
Precisely.
But retraining models can be incredibly resource-intensive, especially for these huge foundation models. What about refining reasoning without retraining during inference? This is test-time behavior optimization, right? Effectively letting models think longer or think harder at runtime.
Precisely. This is crucial when training resources are constrained, or when you're working with API-based models where you don't have access to the internal parameters to fine-tune them. It increases the inference budget, allowing models to engage in more sophisticated thinking at runtime.
More computation at inference time.
Yes. This can be achieved via two main strategies: incorporating external feedback to guide refinement, or generating multiple candidate outputs and using a verifier to select the best one. These two are closely related, as the feedback often acts as that verifier.
Okay, let's break down the feedback-based strategy first. How does an agent leverage external information to improve its reasoning on the fly?
This approach adjusts a model's behavior based on the quality of its generated outputs, relying on a verifier that provides an exact or estimated score. We categorize this feedback into two levels. First, outcome-level feedback.
Based on the final result.
Right, it gives a single score based on the final output. For tasks with a clear ground truth, external tools like compilers in Code or Lever or proof assistance in Boulder can provide accurate feedback. Check if the code compiled or the proof verified.
Objective checks?
When ground truth is unavailable, LLM-based verifiers are trained to assign scores. The challenge here, though, is the sparseness of feedback. It only evaluates the final output, not the journey.
This sounds like it could lead to the unfaithful reasoning problem, where a correct final answer might coincidentally arise from incorrect intermediate steps. How is that addressed?
That's a well-known issue, and it's where step-level feedback comes in. This evaluates each intermediate step during generation, offering finer-grained supervision and directly addressing that unfaithful reasoning problem.
Looking at the process, not just the outcome.
Exactly. Methods like those explored in Wang et al., Zhao et al., and Settler et al. Focus on training process reward models, PRMs, to detect and correct errors throughout the reasoning process. This generally leads to more robust and accurate improvements than just outcome-level feedback, because it guides the model at each crucial decision point along the way.
Much richer signal. Okay, moving on to the search-based strategy for test time optimization. If feedback helps course correct, how do search-based methods help an agent explore a wider, more open-ended problem space?
Well, complex reasoning tasks often have multiple valid solution paths, right? Sometimes you need to explore that space rather than just follow a single chain of thought. Search-based approaches leverage this by exploring several candidate reasoning trajectories in parallel.
Trying out different lines of reasoning.
Exactly. Critic models often guide this decoding process, helping prune less promising paths. For instance, CoTSC, Chain of Thought Self-Consistency, uses a best-of-n approach with majority voting, effectively running multiple thought processes and picking the most common good answer.
Simple but effective.
DBS, Decoding with Beam Search, combines beam search with step-level feedback for more directed exploration. Tree of Thoughts and Core explicitly model reasoning as a tree structure, using Monte Carlo Tree Search, MCTS, for a balanced exploration and exploitation of different branches.
Like game-playing algorithms.
Very similar idea. Forest of Thought generalizes this with multiple trees and sparse activation, and Graph of Thoughts uses even more flexible graph structures for reasoning, allowing for merging paths and more complex exploration. Buffer of Thoughts employs a dynamic memory buffer for meta-level thoughts, providing a dynamic workspace for the agent to reflect and plan.
So lots of sophisticated ways to explore the reasoning space.
Yes, these methods are designed to navigate the complex solution space more effectively, much like an intelligent agent exploring options before committing.
Next up, prompt optimization. We all know LLMs are incredibly sensitive to prompts. The slightest change can have a big impact. What are the core motivations behind systematically optimizing them?
You're absolutely right. LLMs are notoriously sensitive to even minor variations in phrasing, formatting, or word ordering within prompts. This leads to significant changes in their behavior and output quality, which makes designing robust and generalizable AI agent systems incredibly difficult, especially as tasks become more complex.
The prompt engineering challenge.
Exactly, but we want to automate it. Hence, the need for automated prompt optimization techniques to automatically search for high-quality, stable, and effective prompts. Let the machine find the best prompt.
Okay, makes sense. Let's start with edit-based prompt optimization. How do these methods approach the problem? Sounds like tweaking existing prompts.
It is. Edit-based approaches iteratively refine human-written prompts using predefined operations like token insertion, deletion, or substitution. Think of it like fine-tuning the prompt itself. These methods typically treat prompt optimization as a local search problem, aiming to gradually improve quality while preserving the prompt's core semantics.
Small, targeted changes.
Right. GIPS, for example, applies phrase-level edits, subtly changing parts of the prompt. Plum extends this with meta-heuristic strategies for more efficient local search. Tempora even frames this editing process as a reinforcement learning problem, letting the agent learn how to craft better queries based on what works, specifically for query-dependent prompts. The idea is to incrementally improve from a human starting point.
That's a focused approach. But what about exploring a wider, more diverse range of possibilities beyond just editing an existing prompt? That sounds like generative prompt optimization. Starting fresh, maybe?
Pretty much. Generative approaches leverage LLMs themselves to iteratively generate entirely new prompts, often conditioned on a base prompt and various optimization signals. This allows for a much broader exploration of the prompt space, potentially leading to more diverse and semantically rich candidates that a human might not think of.
Using the LLM to improve its own instructions.
Exactly. Optimization signals can include predefined rewriting rules, input-output exemplars, dataset descriptions, prior prompts and their scores, or meta prompts that provide high-level instructions for prompt generation.
So it's about providing the LLM with hints or guidance to generate better prompts. Are there advanced search strategies involved here to make this exploration efficient? Because that space must be huge.
Absolutely huge. And yes, these signals are integrated into sophisticated search strategies like Gibbs sampling, Monte Carlo tree search, as seen in Prompt Agent, Bayesian optimization, like in MIPRO, and neural bandit methods. These strategies enable more efficient and scalable exploration of the vast prompt space.
Okay.
Some researchers go even further, using reinforcement learning to train a policy model specifically for prompt generation, such as Retroformer, which refines prompts by summarizing the root causes of prior failures and suggesting improvements.
Learning from failure to write better prompts. Cool. Then there's text gradient-based prompt optimization, which sounds like a fascinating analogy to gradient descent and continuous optimization, but applied to natural language. How does that work?
It is indeed a very neat idea. This line of work draws inspiration from gradient-based learning but generates natural language feedback, termed text gradients, to guide prompt updates.
Text gradients.
Yeah. The mechanism involves an LLM providing a textual critique of the current prompt's performance, saying why it's bad, and then suggesting an update that moves the prompt in the opposite semantic direction of that criticism.
Like moving downhill in semantic space.
Kind of, yeah. Protigi, for example, uses beam search and banded selection for these gradient descent steps. TextGrad generalizes this to compound AI systems, using LLM-generated suggestions to improve various heterogeneous components, not just prompts. It can even optimize entire configurations across different modules within a complex AI system.
Very powerful if it works generally. And what about treating prompt optimization as an evolutionary process, similar to how biological systems adapt? That's evolutionary prompt optimization.
Here, prompt optimization is framed as an evolutionary process, maintaining a population of candidate prompts that are continually refined through processes analogous to biological mutation, crossover, and natural selection.
Survival of the fittest prompts.
Essentially, yes. EvoPrompt adapts genetic algorithms, GA, and differential evolution, DE, operations for prompts, generating new candidates by combining segments and introducing random alterations. Prompt Breeder takes this further using mutation prompts. These are instructions, either predefined or LLM generated, that specify how task prompts should be modified during this evolutionary process. This allows for creative exploration of prompt space by systematically evolving the instructions themselves.
Evolving the rules of evolution for prompts. Meta. Okay, moving on to memory optimization. Why is this so crucial for agents, especially given the context window limitations and potential for forgetting in current LLMs?
Memory is absolutely essential for agents to reason coherently, adapt over time, and operate effectively over extended tasks. We touched on this earlier. However, LLMs frequently face inherent limitations from their constrained context windows and a phenomenon often termed forgetting, which can lead to context drift and even hallucinations and long interactions. They just lose track.
Right, the context window problem.
Memory optimization focuses on inference time strategies to enhance memory utilization without modifying the underlying model parameters, dynamically deciding what to retain, retrieve, and discard to stay focused and consistent.
Smart memory management. So we're talking about two main objectives, optimizing short-term and long-term memory. Let's start with short-term memory optimization. How do agents manage the immediate, transient information within that limited context window?
Short-term memory optimization manages the limited contextual information within the LLM's working memory. This includes recent dialogue turns, intermediate reasoning traces, and partial results. As context expands, it quickly becomes impractical to retain everything verbatim.
It just won't fit.
Exactly. Strategies include summarization, selective retention of critical information, sparse attention mechanisms, and dynamic context filtering. For example, recursive summarization incrementally creates compact memory representations. MemoChat specifically handles dialogue-level memory, compressing conversational turns. Comedy and Read Agent incorporate extracted or compressed traces for long conversations.
Different ways to compress or select.
Right. Other methods, like MOTI and StructRag, dynamically retrieve self-generated or structured memory, bringing in relevant bits as needed. Memory Bank uses an Ebbinghaus forgetting curve inspiration for hierarchical summarization, prioritizing what's most likely to be relevant based on how humans forget. And Reflection stores episodic insights from past reasoning for self-improvement in future attempts learning from experience.
Learning from specific past episodes.
These methods primarily improve local coherence and efficiency within a single task execution. They keep the agent on track during a task.
Okay, these methods improve local coherence, but as you said, short-term memory isn't enough for knowledge that needs to persist across sessions or tasks. That brings us to long-term memory optimization, the persistent knowledge store.
Exactly. Long-term memory provides persistent and scalable storage beyond immediate context windows, crucially retaining factual knowledge, task histories, and user preferences across multiple sessions. This supports coherent reasoning over extended periods and enables agents to build a cumulative knowledge base.
Building up knowledge over time.
Yes. External memory can be unstructured, like raw text logs, or highly structured, like tuples, databases, or knowledge graphs, spanning diverse sources and modalities. A key aspect here is dynamic memory control mechanisms that intelligently decide what, when, and how to store, update, or discard memory, often based on relevance, utility, or forgetting dynamics. It's active memory management.
Smart curation of the long-term store. Can you give us some concrete examples of these sophisticated long-term memory control mechanisms mentioned in the paper?
Certainly. Matter dynamically selects the most relevant segments from heterogeneous memory sources, maybe a mix of text, database records, etc. AWM enables continuous memory updates in an adaptive fashion. My agent provides memory-aware recall, ensuring that relevant information is retrieved contextually, considering the current task.
Context-aware retrieval.
MIM1 leverages reinforcement learning to maintain an evolving internal memory state, selectively consolidating new information while pruning less useful data. AMEM autonomously organizes and prunes memory, making it more efficient and relevant over time. Mr. Steve hierarchically structures knowledge, mimicking human memory organization for efficient recall.
Hierarchical memory, interesting.
And in collaborative settings, MIRIX introduces 6 specialized memory types for coordinated retrieval, demonstrating how memory optimization scales to multi-agent scenarios where different agents might need different kinds of memory access. These approaches allow agents to proactively manage memory, complementing the short-term mechanisms.
Very sophisticated memory systems. Finally, for single-agent optimization, let's discuss tool optimization. Why are tools so critical for agents operating in the real world, and what are the primary challenges? We know they need them to act.
Right. Tools are critical interfaces, as we discussed. They enable agents to perceive and interact with the real world, access external information, computational resources, and specialized APIs. This makes sophisticated tools use a core competence for solving complex real-world problems that go beyond what an LLM alone can do.
Need those external capabilities.
The challenge, however, is not just exposing agents to tools, but enabling them to intelligently recognize when and how to invoke the right tools, interpret their potentially complex outputs, and seamlessly integrate those outputs back into multi-step reasoning. This requires dynamic decision-making and understanding the tool's function and limitations.
It's not trivial to use tools well. The paper describes two main directions for tool optimization: enhancing agent-tool interaction and, surprisingly, optimizing the tools themselves. Let's start with training-based tool optimization, where you're actually updating the LLM's parameters to make it better at using tools.
Training-based optimization aims to embed tool use capabilities directly into the LLM's internal policy by updating its parameters through a learning process. LLMs aren't inherently trained on tool usage, right? They're trained on text. So this explicitly teaches them how to interact with and orchestrate external functions.
Baking tool use into the model, and within training-based supervised fine-tuning, SFT, seems to be a key method for teaching these interactions, using examples.
Yes. SFT involves training LLMs on high-quality tool use trajectories. These trajectories consist of input queries, intermediate reasoning steps, explicit tool invocations with parameters, and the final answers. Think of them as demonstrations of good tool use.
Learning from demonstration.
Exactly. These act as explicit supervision signals. Tool LLM and GPT-4 tools, for example, leverage powerful LLMs to generate this training data by demonstrating optimal tool use using a smart teacher model to create data for the student. STE uses simulated trial and error interactions to collect effective trajectories, and Tulivo employs Monte Carlo tree search for active exploration to gather even higher quality and more diverse trajectories, ensuring the agent learns robust tool use strategies.
Using exploration to find better examples. What about multi-turn interactions, which can be particularly complex for tool use when an agent needs to use multiple tools in sequence or revisit a tool based on previous results?
That's a known significant challenge. Even advanced LLMs can struggle with complex sequences of function calls and maintaining long-term dependencies in multi-turn scenarios. It gets complicated quickly.
Keeping track of the tool chain.
All right. Magnet synthesizes multi-turn data by generating sequences of queries and executable function calls. Button creates synthetic compositional instruction tuning data via two-stage process to improve multi-turn tool use. API GenMT also uses a two-phase framework to generate tool call sequences and then transforms them into complete multi-turn interaction trajectories through simulated human-agent interplay.
Generating complex training data.
Confucius and Gorilla explore advanced strategies like curriculum learning, starting simple and getting harder, and integrating document retrievers to enhance performance in these complex settings, providing the model with relevant API documentation on the fly.
Smart strategies. And a powerful alternative to SFT, especially for developing adaptive and robust strategies, is reinforcement learning, RL, for tool optimization, learning by doing with tools.
Yes, RL addresses SFT's limitations concerning data quality, coverage, and generalization issues, as handcrafting perfect tool use trajectories for every situation is incredibly difficult, if not impossible.
Hard to cover all cases.
By allowing agents to learn through interaction and feedback, RL facilitates the development of more adaptive and robust tool use strategies that can generalize better to unseen scenarios or new tools. Retool and Nematron Research Tool N1 demonstrate how lightweight supervision in interactive environments can lead to more generalizable tool use.
Learning from interaction signals.
Further research focuses on designing effective reward functions that accurately reflect successful tool use, which is tricky itself, and using synthetic data to ensure stability during the RL training process, which can sometimes be unstable.
Beyond modifying LLM parameters, there's also inference time tool optimization. How does this work to enhance tool use without retraining the core model, maybe for models we can't fine-tune?
Exactly. Inference time optimization enhances tool use without modifying LLM parameters. It typically operates by optimizing tool-related contextual information within prompts or by guiding decision-making through structured reasoning at test time. This approach has two major directions: prompt-based methods and reasoning-based methods.
Okay, let's start with prompt-based tool optimization. Improving how tools are described or invoked via the prompt.
Precisely. Tool documentation and instructions within prompts serve as a crucial bridge between the agent and its available tools. How you describe the tool matters. Prompt-based optimization refines how this documentation is presented and integrated.
Better tool manuals in the prompt.
Essentially, Easy Tool, for example, unifies diverse tool documentation into concise, actionable instructions that are easier for the LLM to process. Draft and play to prompt iteratively refine this tool documentation based on interactive feedback, effectively learning better ways to describe tools by seeing what works and what doesn't.
Learning better descriptions.
A more recent direction explores joint optimization of both tool documentation and the instructions provided to the LLM agent itself, as seen in Wu et al. 2025. This has been shown to reduce computational overhead and improve overall efficiency by ensuring both sides of the interaction, the agent's goal and the tool's description, are optimally configured together.
Optimizing both ends. And finally, reasoning-based tool optimization at inference time, which sounds like it leverages the agent's internal planning capabilities, like the search methods we discussed earlier.
Exactly. Test time reasoning and planning techniques, like tree search, show strong potential for optimizing tool use. Tool LLM validated the React framework for tool use and proposed a depth-first tree search for efficient backtracking when a tool path fails. If one tool call doesn't work, it can backtrack and try another.
Smart exploration of tool sequences.
Toolchain introduces a more efficient tree-based search with a cost function to prune low-value paths, making tool selection more intelligent and resource-aware. Tool Planner clusters tools into logical toolkits, like a web search toolkit or a code execution toolkit, and uses a tree-based planning method for quick reselection and adjustment during complex tasks involving multiple tool types.
Grouping tools logically.
These methods enable more effective exploration and selection of tools during inference, allowing agents to navigate complex tool ecosystems more strategically and efficiently without needing retraining.
Okay, that covers enhancing individual agents. Now let's move on to multi-agent optimization. This truly marks a fundamental shift, doesn't it? From manually designed architectures to self-evolving systems that can automatically discover and refine effective collaboration strategies.
It really does. It reframes the entire workflow design process as a search problem. You're searching across structural space, the topologies, how they're connected, across semantic space, their roles, their instructions, and even across capability space, which LLM backbones to use for which agent.
Searching across structure, meaning, and capability. That's complex.
It is. And what's fascinating here is that the search algorithms range from reinforcement learning and Monte Carlo tree search to generative models and evolutionary strategies. The optimization objectives also expand beyond just raw performance. Now you're explicitly balancing task accuracy, computational efficiency, and crucial safety considerations.
A multi-objective optimization problem.
Exactly. This reflects a deeper understanding that multi-agent systems need to be not just effective, but also robust, efficient, and adaptable in highly complex and dynamic environments.
Let's specifically look at self-evolving multi-agent systems. What's the core motivation here, moving beyond even advanced but still static multi-agent frameworks like AutoGen?
The primary motivation stems from the prohibitively high engineering costs and the limited adaptability of manual workflows in current multi-agent systems. It just takes too much effort to design and maintain them.
The manual bottleneck again.
Right. Self-evolving systems aim to automatically design, evaluate, and refine agent workflows by adapting prompts, topologies, and collaborative strategies based on continuous performance feedback. Instead of hard-coded configurations, workflow optimization becomes a complex search problem over a vast space of possible configurations, spanning from local prompts for individual agents to global topology structures that define how they interact.
Letting the system design itself based on feedback.
That's the core idea.
So the system is actively learning its own structure and interaction patterns, almost like a self-organizing team. That leads us directly to topology optimization. The media matters. This sounds like a crucial insight for scalability and efficiency. How they're connected is as important as what they say.
It is perhaps one of the most critical insights in multi-agent self-evolution. Topology optimization represents a paradigm shift because it recognizes the communication structure itself as a powerful and highly influential optimization target.
The connections themselves are key.
Absolutely. The fundamental observation, as the paper notes, is that even the best prompts cannot compensate for poor architectural choices. You can give agents perfect instructions, but if their communication network is inefficient or ill-suited, performance will suffer dramatically.
Makes intuitive sense.
Existing work in this area clusters into two families: program code-level workflow topologies and communication graph topologies.
Okay, optimizing code versus optimizing the connection graph. Can you give examples of how these different types of topologies are optimized?
Sure. For code-level workflows, systems like Autoflow generate and refine self-adaptive workflows directly defined in code. allowing for programmatic evolution. The system writes and rewrites its own interaction logic. Offlow and scoreflow focus on self-correcting flows that adjust execution based on outcomes. MAS-GPT offers flexible orchestration by enabling LLMs to dynamically define and adapt multi-agent programs.
Evolving the workflow code.
Right. For communication graph topologies, approaches like GPT-Swarm focus on dynamic swarm formation, where agents can reconfigure their connections on the fly, like a swarm adapting its shape. Dynaswarm enables adaptive topology changes based on needs, and GDesigner synthesizes optimal graph structures based on task requirements, much like optimizing a network layout for efficiency.
Finding the best wiring diagram. And what about methods for streamlining these communication networks? Ensuring efficiency and avoiding redundancy or even security risks seems vital if they're self-organizing.
That's where pruning methods come in. They optimize topologies by removing redundant, inefficient, or risky communications while preserving essential collaboration channels, cutting out the noise.
Smart pruning.
Agent Prunes, for example, prunes spatial temporal communication graphs, using a trainable, low-rank guided graph mask, explicitly optimizing for token economy by minimizing unnecessary communication-saving compute and cost. AGP, adaptive graph pruning, extends this by optimizing both agent quantity, hard pruning removing agents entirely, and communication edges, soft pruning removing connections, per task, adapting the team size and interaction intensity dynamically.
Adapting team size and connections.
On the critical safety front, methods like GSafeGuard and NetSafe actively prune communication edges, specifically to fortify security against adversarial attacks and to analyze topological safety risks, ensuring that self-evolution doesn't inadvertently open new vulnerabilities.
Pruning for safety, that's important. Next, we have unified optimization, which recognizes that prompts and topology are deeply interconnected, not independent choices. It's not enough to optimize one in isolation.
This is a key insight, yes. You can have a perfectly optimized prompt, but if the agent receiving it is in an inefficient or inappropriate communication structure, that prompt's effectiveness will be severely limited. Conversely, an elegant topology is useless with poorly instructed agents. This interdependence, this coupling, has led researchers to develop approaches that explicitly tackle joint optimization of these elements.
Optimizing prompts and structure together. How is that done? What are the main approaches within unified optimization that tackle this interconnected design challenge?
We primarily see two approaches mentioned. First, code-based unification, where prompts, roles, and topology implicitly co-evolve through code generation and refinement. AA, Autonomous Development Agent System, uses code to synthesize self-adaptive workflows, allowing the agent system to essentially write its own operational logic, including roles and interactions. Flow Reasoner focuses on self-refining execution, where the agent continuously adjusts its workflow code.
Evolving the code that defines everything?
Right. More explicitly, search-based approaches develop explicit mechanisms for coordinating prompt and topology design within defined search spaces. Evo Agent, for instance, defined its search spaces as textual agent settings, covering roles, skills, and prompts, and then uses evolutionary algorithms, mutation, crossover, and selection to optimize both the individual agent instructions and their interaction patterns simultaneously.
Evolving text descriptions of the whole system.
EvoFlow also uses evolutionary search, but over operator node workflow graphs. It introduces composite operators like chain of thought and debate as building blocks in the graph, and crucially treats LLM selection itself as a decision variable. This allows for cost-performance Pareto optimization, finding solutions that are good compromises between being effective and being resource efficient.
Balancing cost and performance during evolution. Very practical.
Wow.
Finally, let's talk about LLM backbone optimization within a multi-agent context. This aims to enhance the core competencies of the agents themselves, specifically for collaboration, right? Making them better team players.
Exactly. Here, the focus is on collaboration-oriented optimization. The fundamental assumption is that vanilla LLM agents aren't inherently effective team players. They haven't necessarily been trained for nuanced communication, negotiation, or conflict resolution needed in multi-agent settings. So they require targeted training to excel in these collaborative behaviors.
Training them to collaborate.
Yes. Copper, for example, trains a shared reflector model that provides role-aware, personalized reflections, helping agents better understand their own contributions and the team's state, like a coach giving feedback.
Interesting.
Optima directly targets communication efficiency via supervised fine-tuning, direct preference optimization, DPO, and hybrid methods. They show significant performance gains with reduced token costs, which is a major operational benefit in large systems. Maperel introduces reinforcement learning signals within multi-agent debate frameworks to explicitly elicit and reinforce collaborative behaviors, encouraging higher quality and more frequent communication, thus transforming individual agents into better team members.
We've covered a lot of ground on optimizing agents, both single and multi. Now let's pivot to a critically important area for practical deployment and trustworthiness. Evaluation, safety, alignment, and robustness in these lifelong self-evolving agents. This seems incredibly challenging. How are we assessing these increasingly complex and autonomous systems?
Evaluation methodologies are definitely evolving rapidly to try and keep pace with agent capabilities. It's moving far beyond simple accuracy metrics. For web navigation and browsing agents, benchmarks like BrowseComp, Web Arena, and the multimodal visual Web Arena test not only navigation success, but also adaptability to interface changes and text-visual integration. They often incorporate intermediate metrics like clicks or correct form fillings.
Measuring the steps along the way.
Right. However, reproducibility and generalization remain challenging due to the web's inherently dynamic and often unstructured nature. Benchmarks can go stale quickly.
True. And for systems with multiple agents where collaboration and coordination are key, how do we measure teamwork?
For multi-agent collaboration and generalists, benchmarks such as multi-agent bench and swarm bench evaluate collaboration, competition, and decentralized coordination. They assess both task completion and the quality of inter-agent communication. Are they working together effectively?
Quantifying teamwork.
Generalist benchmarks like GAIA and Agent Bench test adaptability across highly diverse environments, web browsing, coding, database interaction, pushing agents to perform across a broad range of tasks. The challenge lies in aggregating metrics across such heterogeneous tasks and avoiding the risk of overfitting to specific benchmark settings. You don't want agents good only at the benchmark.
Right, the generalization problem. What about agents interacting with visual interfaces or combining different modalities of input, like on a smartphone?
GUI and multimodal environment agents are evaluated on benchmarks like Mobile Bench, Android World, and Osworld, which simulate realistic apps and operating systems. These require complex action sequences, combining natural language understanding, visual perception, and API invocation.
Testing real-world app usage.
Exactly. Evaluation measures task success, state management, and adaptability to GUI changes. But standardization and reproducibility are difficult due to the inherent variability of user interfaces across different systems, versions, and screen sizes. An agent working on one Android version might fail on another.
Brittleness is a major issue there, and for highly specialized applications where domain-specific knowledge and constraints are paramount, like in science or medicine.
Domain-specific task agents are evaluated with tailored benchmarks that reflect their unique operational contexts. SWE Bench, for example, evaluates code editing agents on real GitHub repositories, assessing their ability to fix actual bugs submitted by humans.
Real-world coding tasks.
DataSpinch and MLGym are designed for data science agents, testing their ability to perform analysis and build models. Agent Clinic and MAgent test multimodal reasoning in complex clinical settings, assessing diagnostic accuracy and adherence to medical protocols.
High-stakes domains.
Absolutely. Evaluation criteria here extend beyond binary success to include things like test pass rates for code, policy adherence, and strict domain-specific constraints. Inconsistencies in metric definitions and generalization gaps to real-world deployment scenarios remain significant challenges across all these domain-specific areas.
This all sounds like a lot of human effort in benchmark creation and scoring. Is there a way to leverage AI itself for evaluation? That leads us to LLM-based evaluation, specifically the intriguing concept of LM as a judge, using AI to grade AI.
Exactly. The LM as a judge paradigm employs large language models to assess the quality of outputs from other AI systems using carefully structured prompts. This offers a highly scalable and cost-effective alternative to relying solely on human judgment or static, often simplistic metrics, which frequently fail to capture the semantic depth and nuance of complex agent outputs.
Faster and cheaper evaluations.
Potentially, yes. LLM judges can operate in point-wise evaluation, scoring outputs against criteria like factuality or coherence, or in pairwise comparison, selecting a preferred output between two options and providing a detailed justification. I prefer A because.
Okay, so it's faster and cheaper, but what are the inherent limitations? Is an LLM really a reliable judge of another LLM's output?
That's the million-dollar question. LLM-based evaluations are known to be sensitive to the precise phrasing and design of the prompt used for judging. They can also be susceptible to biases present in their training data, or inherent to the LLM itself, like position bias or verbosity bias.
Biases in the judge.
Furthermore, single-step, output-focused evaluations can easily overlook the reasoning depth and intermediate steps involved in complex multi-step processes, providing only a superficial assessment. Did it get the right answer for the wrong reason?
The unfaithful reasoning problem again.
Exactly. To address this, enhancements like multi-agent deliberation frameworks, such as Collabial, where multiple LLM judges debate, and structured meta-evaluation benchmarks are being developed to calibrate and improve their reliability and provide more comprehensive assessments.
Trying to make the judging more robust. What if we take it a step further and use a full-fledged agent to judge other agents? That's agent as a judge, which seems to get closer to the kind of complex evaluation required for self-evolving systems that involve processes, not just outputs.
Yes, the agent as a judge framework extends LLM-based evaluation by employing full-fledged agentic systems, capable of multi-step reasoning, state management, and tool use, specifically to critique other AI agents. The key difference here is that agent judges evaluate the entire reasoning trajectory, not just the final outputs.
Evaluating the whole process.
Right. This allows them to capture the decision-making processes, intermediate actions, and internal states of the agent being evaluated, providing a far more holistic assessment. For example, the paper mentions an agent judge on the DVI benchmark for code generation agents. It incorporated specialized modules to analyze intermediate artifacts, validate reasoning graphs, and perform hierarchical validation of code.
A specialized judge agent. And what were the results of using such an advanced agent for evaluation? Did it work well?
According to the research cited, this led to evaluations that aligned more closely with human expert judgments and delivered substantial efficiency gains compared to manual review. So it offers significant promise for scaling up evaluation in complex domains.
Promising.
However, implementing agent as a judge introduces additional complexity in its own design and deployment, and challenges remain for its generalization to domains beyond code generation, where the ground truth or desired behavior might be less clearly defined.
Still early days for generalizing agent judges. Now let's connect this back to our guiding principles, specifically the Endure Law. Safety, alignment, and robustness in lifelong self-evolving agents. This isn't a one-time compliance check at the start, is it? It has to be ongoing.
Absolutely not. For lifelong, self-evolving agentic systems, safety is an ongoing, continuous requirement. Every evolution step, from a subtle prompt update to a major topology change, must be continuously assessed for unintended or malicious behaviors. This demands evaluation protocols that are dynamic, granular, and scalable, ensuring agents remain aligned with their objectives and human values throughout their adaptive lifecycle. Safety isn't a feature you add at the end.
It has to be baked in and constantly monitored. What kind of benchmarks are being developed to specifically probe for these risks in continuously evolving agents? How do you test for emergent bad behavior?
Risk-focused benchmarks are becoming crucial. Agent harm, for instance, measures an agent's propensity to comply with malicious multi-step requests, revealing how even powerful LLMs can be coaxed into performing complex, unsafe behaviors like planning fraud or cybercrime, if you ask cleverly.
Probing for harmful compliance.
Domain-specific probes like red code specifically target code security vulnerabilities generated by agents, while Mobile Safety Bench focuses on unsafe actions in mobile control, stress testing agents in sandboxed environments. Behavioral probes like Machiavelli explore whether agents develop unethical, power-seeking strategies when driven by reward optimization, highlighting the complex interplay between ensuring performance, excel, and maintaining safety, endure. Can optimization lead to bad strategies?
The alignment problem in action. And those meta-evaluation approaches we mentioned, like agent as a judge, do they help with safety monitoring, or do they have their own limitations here too?
Yes, meta-evaluation approaches like agent as a judge, agent of vol, and R-judge can position LLM agents as evaluators or safety monitors, offering scalable oversight. That's the promise. But these studies also expose the limitations of current risk awareness. Over-reliance on correctness metrics can conceal deeper epistemic risks and systemic biases that are not immediately obvious from the output. An answer might look correct but be based on flawed or biased reasoning.
Hidden risks?
And legal alignment tests like Safe Law Bench demonstrate that even state-of-the-art models struggle with established legal principles, reflecting the inherent difficulty of codifying and enforcing alignment in open-textured norm domains where rules are complex and require interpretation.
Hard to teach nuanced rules. So the urgent challenge for MOSTI is making safety evaluation itself dynamic and continuous, moving beyond static one-off audits before deployment.
Precisely. Most current evaluations are snapshot-based. Check it once, ship it. For an AC systems, safety evaluation must become truly dynamic, continuously monitoring, diagnosing, and correcting behaviors as the system evolves. Developing longitudinal, evolution-aware benchmarks that track safety, alignment, and robustness across the full life cycle of an agent ecosystem remains an open and urgent challenge, directly addressing the core of the Endura law. How do you ensure safety while it's evolving?
We've covered the foundations, the framework, the optimization techniques, and the critical aspects of evaluation and safety. It's a complex picture. Now let's explore the challenges and future directions, a roadmap for these lifelong systems. Let's group the current challenges by the 3 laws, as the paper suggests, starting with indoor safety adaptation. What are the big hurdles there?
Within Endure, a primary and deeply complex challenge is safety, regulation, and alignment. We just touched on this. Current optimization pipelines often prioritize performance metrics over inherent safety, which can lead to critical risks like unintended behaviors, privacy breaches, and misaligned objectives that are hard to detect early, especially as systems evolve in unexpected ways.
Optimization overriding safety.
And the dynamic nature of evolving agents also fundamentally undermines static, legal, and regulatory frameworks. How do you regulate something that's constantly changing itself? This necessitates entirely new evolution-aware audit mechanisms, adaptive licenses, provable safety sandboxes, and legal protocols to effectively track and constrain an agent's self-directed evolutionary path.
Regulation needs to evolve too.
Absolutely. And what about the stability of the entire system during this continuous adaptation? That sounds like a significant hurdle for trustworthiness.
Yeah, if it's constantly changing, is it stable?
That's the second challenge under Endure. Reward modeling and optimization instability. Learn-to-reward models, particularly those used for intermediate reasoning steps, often suffer from data scarcity, noisy supervision, and feedback inconsistency. This can lead to unstable or even divergent agent behaviors over time. One small change in the reward model could send the evolution off course. Stability is absolutely central to trustworthiness.
Unstable evolution is dangerous.
Exactly. Even small perturbations in inputs or update rules can significantly undermine an evolving workflow, making the system unreliable in critical applications.
Moving on to Excel performance preservation. What are the challenges here, particularly in specialized fields where traditional metrics might be elusive or controversial?
One key challenge is evaluation in scientific and domain-specific scenarios. In highly specialized fields like biomedicine, material science, or law, obtaining reliable ground truth for validation is often difficult, expensive, or even subject to expert dispute. What is the right answer or the best approach?
No easy answers.
This significantly complicates the construction of trustworthy and objective feedback signals that are essential for guiding optimization and ensuring performance preservation, the Excel law. How do you know if you're preserving performance if you can't measure it reliably?
Good point. And for large-scale multi-agent systems, there's always a big trade-off to consider between raw performance and the resources required. Efficiency matters.
Absolutely. Balancing efficiency and effectiveness in multi-agent system optimization is a significant hurdle. While large-scale multi-agent optimization can lead to impressive performance gains, it often incurs substantial computational cost, increased latency, and potential instability due to complex interactions. More agents mean more compute, more communication overhead.
The cost of complexity.
Designing methods that explicitly model and intelligently trade off effectiveness against efficiency under strict latency, cost, or energy budgets remains an unresolved problem for practical deployment. We need agents that are not just smart, but also affordable to run.
Right. And a practical concern for any optimized component prompts, topologies, whatever, is its generalizability. How well do these optimized artifacts transfer to new situations or different models?
Yes, the transferability of optimized prompts and topologies is a persistent challenge. Optimized prompts or agent topologies are often brittle. They show poor generalization across different LLM backbones with varying reasoning abilities, or even across slightly different task distributions. An optimized prompt for GPT-4 might not work well for Llama 3, or vice versa.
Optimized for one specific context.
This fundamental brittleness undermines scalability and reusability, making it difficult to deploy these optimized components broadly in real-world production settings without extensive retuning for every new model or minor task variation.
Finally, for Evolve Autonomous Optimization, what are the key challenges preventing full, truly autonomous self-evolution, especially in complex real-world environments beyond text?
First, there's optimization in multimodal and spatial environments. Most current optimization algorithms and agent frameworks are predominantly text-only. However, Real-world agents need to perceive and process rich multimodal inputs, vision, audio, tactile data, and reason in spatially grounded or continuous environments, like a robot navigating a room.
Interacting with the physical world.
This requires the development of sophisticated internal world models and robust perceptual temporal reasoning capabilities that are largely missing in current self-evolutionary loops. How does an agent evolve its understanding of physics or space?
Big challenge. And the tools themselves, it's not just using them effectively, but the agents proactively adapting and even creating new ones. That sounds like a massive leap.
Exactly. Tool use and creation is another critical challenge. Current methods typically assume a fixed, predefined tool set that agents learn to invoke. Okay, here are your tools, learn to use them. However, true autonomous evolution should encompass the crucial aspects of autonomous discovery of new tools, adaptive modification of existing tools, and even the co-evolution of tools alongside the agents themselves.
Agents becoming toolsmiths.
Precisely. This pushes towards agents that are not just users but also designers of their own capabilities, figuring out what new functions they need and how to build or acquire them.
So, given these formidable challenges across Endure, Excel, and Evolve, what do these point to in terms of promising future directions for researchers and practitioners in this field? Where should the effort go?
Many of these limitations highlight clear and exciting research avenues. One is developing simulated environments for fully autonomous self-evolution, MAS. This means creating open-ended, interactive, and high-fidelity simulation platforms, like sophisticated virtual worlds where agents can iteratively refine prompts, memory, tools, and entire workflows via truly closed-loop optimization, without the risks and costs of real-world deployment during the learning phase.
Safe sandboxes for evolution.
Exactly. Another major direction is advancing tool use and creation, MAO/MAS. We need to move beyond static tool invocation towards agents that adaptively select, dynamically compose, or even autonomously create new tools, integrating reinforcement learning and feedback-driven strategies with robust evaluation pipelines to facilitate this meta-level capability.
Empowering agents to expand their own skills.
Yes. What about making evaluations more reflective of real-world scenarios and enabling continuous monitoring, addressing the evaluation gap? That's real-world evaluation and benchmarking, cross-stage. The goal here is to create benchmarks and protocols that truly reflect real-world complexity, support interaction-based and longitudinal assessment testing over time, and align with the long-term improvement signals necessary for lifelong learning, moving beyond static, single-shot test sets.
More realistic and continuous testing.
And tackling that efficiency-effectiveness trade-off in multi-agent systems, which is so critical for practical deployment.
Definitely needed.
That's another key direction.
Yeah.
Effectiveness-efficiency trade-offs in MAS optimization, MAO. This involves designing optimization algorithms that jointly model both performance and critical resource constraints, like latency, cost, and energy consumption. This will enable MAS deployment under realistic, strict operational budgets. Pareto optimization for agents.
Making them practical to run at scale. And finally, a very tailored approach for specialized fields like science, medicine, or law, where the context is king.
Yes, domain-aware evolution for scientific and specialized applications, MASE. This means tailoring evolution methods to the unique, stringent domain-specific constraints in areas like science, medicine, law, or education. It involves integrating heterogeneous knowledge sources, like scientific papers or legal statutes, designing bespoke evaluation criteria, what does success look like in drug discovery, and ensuring strict regulatory compliance throughout the evolutionary process.
Custom evolution for specific domains. The outlook sounds incredibly ambitious, but also incredibly promising. It's a true call to action laid out in this paper.
It is. The roadmap involves creating optimization pipelines that are not only high-performing and deeply domain-adaptive, but also inherently safe, fully regulation-aware, and entirely self-sustaining. Embedding these solutions within the MAO power trajectory and grounding them firmly in the three laws of self-evolving AI agents offers a coherent and compelling path toward truly lifelong autonomous agentic systems. Systems that can endure, excel, and evolve across their full operational lifetimes.
What an incredible journey we've taken today. We've delved deep into the exciting trajectory of AI agents, moving from static, pre-trained models all the way to dynamic, self-evolving ecosystems.
That's a huge leap.
You've now gained, hopefully, a comprehensive understanding of the conceptual frameworks, the diverse optimization techniques, and the crucial evaluation considerations that define this paradigm shift.
And remember the three laws of self-evolving AI agents: endure, excel, and evolve. These aren't just theoretical constructs. They are fundamental design constraints, acting as the guardrails for the AIC paradigm.
The essential rules.
They guide research from narrow, single-shot optimization toward continuous, open-ended self-improvement, ensuring that as AI agents gain autonomy, they do so safely, effectively, and adaptively.
The ability for agents to truly endure, excel, and evolve will be decisive in real-world scenarios, whether it's accelerating scientific discovery, streamlining software engineering, or fundamentally enhancing human-AI collaboration.
It changes the game.
This survey paper is both a comprehensive reference and really a powerful call to action to build an ecosystem of self-evolving AI agents that don't just execute tasks, but live, learn, and last.
Live, learn, and last. So as we pave the way for truly autonomous, resilient, and trustworthy lifelong agentic systems, what profound societal and technological implications do you foresee when AI agents can continuously redefine and improve their own existence within our complex world?
That's the good question.
What does it mean for us when our tools literally begin to live and evolve in such a profound way? Something to think about.